So in this video and subsequent videos, I'd like to give an introduction to axiomatic set theory. So in particular, I'd like to talk about the ZFC axioms. The ZFC axioms stand for Zermelo-Fraenkel with the axiom of choice, and we'll talk about what the axiom of choice is in a couple videos. But before I start, I want to talk and give an example about what it is we're actually trying to do, or what it is set theory is doing. So set theory is an attempt to give a foundation of mathematics, of modern mathematics. Foundation of modern math. What does this mean exactly? It means that we're able to encode modern mathematics into set-theoretic language. Into set-theoretic language. For example, what if an important object in mathematics is an ordered pair. So, ordered pair. Or I guess an ordered n-tuple or an n-tuple or something, but in particular an ordered pair. So, given, this will be a bit of an informal definition because we don't formally know we're able to do this, but believe me that we're able to. So given a set, two sets x and y, this is a definition in air quotes. We define the ordered pair x comma y as the unique set. Let me write this down first. So this is the set of the set x and the set x comma y. Now, it might look confusing. So why would I define the ordered pair as this particular set? So question, why? And the reason why is that it satisfies an important property. So I'll write it again. So important property. I don't know if that's actually the abbreviation for important, but that's what I'm making it to be. Important property is that if two ordered pairs equal each other like this, we'd expect that the first coordinate is equal to this. The first coordinate of this one is equal to the first coordinate of the other ordered pair, and similarly with the second coordinate. And that's actually precisely what we have. So this is an important property that the previous definition, I'll write it again. This is the definition of an ordered pair. This definition satisfies this important property. So I can sketch a proof. So sketch a proof Okay, so going this direction is easy. X equals A and X equals B. Sorry. So the first direction is easy because if we have that X is equal to A and Y is equal to B, then we really just substitute in the X for A in here and then the Y for B in here, and we get that this condition holds. Okay, so going the other direction is again, so the goal, or what we're trying to show, is that if we have this condition, that implies that X is equal to A and Y is equal to B. This symbol means and, if you weren't familiar with it already, or if you didn't know. Okay, so how do we do this? There's two cases. Case 1 is what if X is equal to Y? Well, X and Y are both sets, so they're either equal to each other or not equal to each other. Well, if we have this, well, this implies that X comma Y, well, that's by definition equal to this set. What is this set now? This set is just equal to this because X and Y are equal to each other. So the set of X comma X is just another way of writing this, or it's convention for this set. And this is just equal to this particular set because these two sets are the same. So we have that X comma Y is equal to the set X, the set containing the set containing X. And this is supposed to be equal to, this is equal to the ordered pair A comma B, which is by definition equal to this. So this implies that in particular we have that the set containing X is equal to the set containing A comma B, which further implies that A is equal to X, which is equal to B, which is equal to Y, which is exactly what we want. Okay, so that was case 1. Case 2 is what if X is not equal to Y? Let me write that again. So what if X is not equal to Y? Well, if X is not equal to Y, then first we know that A isn't equal to B. And why do we know that? Well, if A were equal to B, then we could repeat that same argument for case 1 and then get that X is equal to A and Y is equal to B, but they're both equal to each other. So then we have that X is equal to Y as well. Okay, so we know that since we know that the two ordered pairs are equal to each other, we know we have this equality. So looking at the first set, that means that the set X is equal to one of these elements in this set here. But because A is not equal to B, we can't have that this set here is equal to, we can't have this equality because this has one element and this has two elements. Or if they were equal, then A would be equal to X and would be equal to B. So A would be equal to B. So we know, so then we have to have the set containing X is equal to the set containing A, which implies that X is equal to A. Similarly, because X isn't equal to Y, we can't have that the set X comma Y is equal to the set containing A. So we have to have this. So that means that in particular y, the element y, is equal to either a or b. But if it were equal to a, then we'd have that x is equal to y. But we've assumed that we can't, that's not true, so we have to have instead, so that means that y has to be equal to b. But that's exactly what we wanted, so we're done.